Welcome. So we are ready to continue now and look at our F distribution. So an F distribution, it's named after an English statistician named Sir Ronald Fisher. So the Fisher is the F part. And this F statistic we saw is created by estimating population variance in two different ways. One is called the mean square between, and the other is called the mean square within, or mean square error. So the way it works is that if there's no significant difference between population means for a group of populations, then we expect that numerator and denominator approximation for our variance to be about equal. And that would mean that the value of F is close to 1. However, if the population means are not equal, then the numerator, the mean square between, is going to estimate a quantity larger than the population variance that's common to these three populations. So as the mean square between increases, this F statistic will also increase. So an ANOVA test will always be a right tail test because the values here will always be positive, and the larger the numerator gets, the more evidence we have that the means are not equal. All right, so we're going to continue this with our study that we did on satisfaction ratings of teachers. So I've repeated the values we already wrote previously for the F statistic, so the test statistic or test value, and then degrees of freedom in the numerator and denominator. All right, so our p-value, so because it's a right tail test, it will be the probability of an F statistic being larger than our test value of 8.182. So if we want to find that probability, now it's FCDF, and then we're going to have those 4 inputs. So let me write down what it will look like on our calculator. So F distribution, CDF will find area or probability. It's a right tail test, so our lower limit will be our test value or test statistic, so 8.182. And then F distributions do continue without bound as the value for F gets larger. There is no limitation to how large it can get, so that's our infinity. So in theory, F could be anywhere indefinitely to the right. And then we need our degrees of freedom of our numerator, which was 2, and degrees of freedom of our denominator, which was 12. All right, so let's find our FCDF. So we'll go to our distributions. And then I'm just going to scroll down here. So you'll find your FCDF. And then we're going from 8.182 to our infinity, and then lower bound, I'm sorry, not lower bound, upper bound, but degrees of freedom. So it was lower bound, upper bound, and then degrees of freedom of our numerator, degrees of freedom of our denominator. All right, and there's our p-value, 0.0057. So 0.0057. And I'm going to write that as a percent. So 0.57%. So even less than 1%. So at a 5% significance level, so our p-value there, 0.57%, is definitely less than or equal to our alpha of 5%. So when our p-value is low, we let the null go. So our decision will be reject the null hypothesis. And as always, when we reject the null, we are supporting our alternative, which for us was our claim. So at a 5% significance level, we can conclude that at least one type of school has a mean teacher satisfaction rating that is significantly different from the others. Okay, so let's do another one. And we are going to take a look at a problem where this time I don't have the original data. They've just done the summary for me. All right, so let's take a look. So it says a recent survey asked 1,130 respondents, what is the highest level of education you've completed? And if you're employed full time, how many hours do you spend working at your job during a typical week? To decide if there are any differences in the mean hours per week worked by these different groups, an ANOVA test was run, and it resulted in an F statistic of F approximately 2.14. So they've already run the ANOVA test and given us their F statistics. We don't have to do that ourselves. So in this example, these sample summaries are given. So they did not give me the original data, but let me just look at, here I'll look at people that have completed graduate school. So they looked at 283 people that completed graduate school, and on average, they worked 42.2 hours during a typical week with a sample variance of 106.6. Okay, so our null hypothesis would be that the population mean hours worked in a typical week for people that have less than high school education is the same as the hours per week on average for people with a high school education, and then is equal to the mean for those with bachelor's degrees, and that's the same as the mean of those with graduate degrees. Okay. And then the alternative will be that not all of these population means are equal. All right, so in running an ANOVA test, so K is the number of treatments, or in this case, you can think of these as the number of different populations of interest. So we're looking at 4 different populations. Capital N is the grand total number of observations. So overall, in total, they do say 1,130 respondents, but I'm just going to check that. So 282 plus 279 plus 286 plus 283 does indeed give me, so this total was the 1,130 people that participated in the study. So that's where that capital N comes from. So I'm just going to write down what I did here in the notes. So if I add up those individual sample sizes, that's the 1,130. So this would be sample size for population 1 plus sample size for 2, for 3, etc. So we sometimes just refer to that as the grand total. All right, so then let's go to the parameters that we need that describe this particular F distribution. So 2 degrees of freedom. Degrees of freedom in the numerator is K minus 1. So we had 4 populations, so 4 minus 1 would be 3 degrees of freedom for the numerator, and degrees of freedom for the denominator is your grand total number of observations minus K, the number of populations that are under consideration. So 1,130 minus 4 is 1,126. And then our p-value. So before I find the p-value, I'm just going to draw this graph. So our test value or test statistic, 2.14. So this doesn't have to be perfect. So that's our test value. So looking at our F distribution, the p-value, because ANOVA is a right tail test, the p-value is the area to the right of the test value. And that's what we're going to find now. So the p-value is the probability of F being greater than 2.14. All right, so our entry will be FCDF. Our lower bound would be our 2.14. Upper bound is infinity. Degrees of freedom of the numerator was 3. Degrees of freedom of the denominator 1,126. All right, so we go to our distributions. And I'm just going to scroll down again. FCDF 2.14, B99, 3, 1,126. Okay, and that's looking like 0.935. So 0.0935, or as a percent, 9.35%. Right, and we're going to make our decision at a 5% significance level. So 9.35%. If we're using that alpha, that is definitely bigger than alpha. So our p-value is not low. So we do not reject the null. We do not have strong enough evidence against the null. And that means we do not support our claim. All right, so at a 5% significance level, we cannot support a claim that at least one of the groups has a mean that differs significantly from the others. All right, so if you're given a problem where they give you the F statistic, you don't have to complete an ANOVA test yourself. You just work with that F value and find your p-value using your FCDF on your calculator.